Chapter 8, Part 2. In this section, we're going to take a look at how we can organize algebra tiles into perfect rectangles and then factor out their dimensions. So we're going to be going the opposite of how we went a couple of chapters ago when they gave us the outside of the rectangle and we multiplied to find the insides. So we're going to take this group of tiles and we're going to organize them in a perfect rectangle. We're going to put this x squared in the lower left-hand corner. I see 1, 2, 3, 4, 5, 6 x's, so we're going to evenly split them. We're going to put 3 above. And 3 to the right. And then we're going to fill this space with our singles. There's 1, 2, 3, 4, 5, 6, 7, 8 singles. So if we try and fill the gap, the problem is that the way I have it currently arranged, I would need 9. And I only have 8. So I gotta rethink. Okay, so what if I move one of my x's? And I put 2 on the top and 4 on the side. Now I have room for 8 singles, which is perfect. 1, 2, 3, 4, 5, 6, 7, 8. So there's my rectangle. And now I can factor out the dimensions. So this dimension, well, this is of length x, this is of length x, so we get x squared. This is of length 1, so that because it's x units, this way x times 1 gives you the x. And then we have 1, 1, 1, 1, so that we've got x plus 2 by x plus 4. So the product of x plus 2 times x plus 4 equals x squared plus six x plus the 8. So let's take a look at a couple of rectangles that are already built, and we just have to pull out the dimensions. So 2x and 6x squared, both divisible by 2x, 5 and 15x, both divisible by 5, so I pull out a 5. 2x and 5, the only thing they have in common is 1, and I can also think about it as 1 times 2x gets me the 2x, and 1 times 5 gets me the 5 I need there. So then I'm focused on this row, 6 and 15. Well, 3 goes into 6, it also goes into 15, and they both have an x. So we can write it out as 3x plus 1 times 2x plus 5 equals 6x squared plus 17x plus 5. For letter B, negative 2y and negative 6 are both divisible by negative 2. 5xy and 15x are both divisible by 5x. Negative 2y and 5xy both have a y in common. Negative 6 and 15x both divisible by 3. So we have y plus 3 times 5x minus 2 equals 5xy plus 15x minus 2y minus 6. Letter C. So negative 9x and negative 12x. We've got They're both divisible by -3. 12x squared and 16x. They're both divisible by 4x. -9x and 12x squared. Both divisible by 3x. -12 and 16x. Both divisible by 4. And you check yourself. 3x times 4x is 12x squared. 3x times -3 is -9x. 4 times 4x is 16x. 4 times -3 is -12. So it's 3x plus 4 times 4x minus 3. And that equals 12x squared plus 7x minus 12. So the key is to look at each row and pull out what they have in common, and every column what they have in common, and then stop to double check. Make sure 2x times 3x gives you 6x squared, 2x times 1 gives you 2x, 5 times 3x is 15x, 5 times 1 is 5. While working on the previous problem, Casey noticed a pattern with the diagonals of each generic rectangle. However, just before she shared her pattern with the rest of her team, she was called out of class. The drawing on her paper looked like the diagram below. Can you figure out what the two diagonals have in common? Well, they don't have a common factor. These two both have an x, but these two don't. So let's think about some operations we could do with them to check. Well, 2x plus 15x gives us 17x. But on the other diagonal, we don't have like terms, so we wouldn't be able to combine. So it's not addition, it wouldn't be subtraction for the same reason. Let's see what happens when we multiply them. So if we take 2x times 15x, let's see if that's the same as 6x squared times 5. So 2 times 15 is 30, x times x is x squared. 6 times 5 is 30, so we have 30x squared. So the product of the two diagonals are equivalent. Does this pattern always work? Let's go back to the previous problem and verify about the products of each diagonal. So if we take the left diagonal and multiply those two numbers, and we take the right diagonal and multiply those two numbers, do we always get the same thing? Let's see. So the first one in number 10 is the example they had given us. So that one we already checked. Letter B, so if we take 15x times -2y, does that equal 5xy times -6? Well, we get -30xy equals -30xy. So yes, this diagonal has the same product as this diagonal. Let's try letter C. So the left diagonal is -9x times 16x. Checking to see, does that equal 12x squared times -12? Well, we get -144x squared, because -9 times 16 is -144. X times x is x squared. -12 times 12 is -144, and then we have our x squared. So it checks for that one as well. So it turns out Casey's theory is right. The diagonals products should always be equal. If you've properly set up your generic rectangle, that will always be true. So here's a little summary. Why does Casey's pattern work? So why does the product of the terms in one diagonal of a 2x2 generic rectangle always equal the product of the terms in the other diagonal? Examine the generic rectangle given for a plus b times c plus d. Notice that each of the resulting diagonals have a product of a, b, c, d. Thus, the product of the terms in the diagonals are always equal. So because you have a common factor here that comes out here, and you have a common factor that comes out here, and a common factor here, and a common factor here, the two diagonals have the same basic factors, so their products are always going to be equal. some vocabulary for expressions. Since algebraic expressions come in several different forms, there are special words used to help describe these expressions. For example, if the expression can be written in the form ax squared plus bx plus c and a is not 0, it's called a quadratic expression, and that's the focus of Unit 8. So here are some examples: x squared minus 15x plus 26, 16m squared minus 25, 12 minus 3k squared plus 5k. So they're all quadratic because they have the squared term. The way an expression is written can also be named. When an expression is written in product form, it is said to be factored. Factored means you have something times something else. So when you have x squared minus 15x plus 26, it factors into x minus 13 times x minus 2. So x minus 13 and x minus 2 are the factors of the original expression. These are the two things we have to multiply to get this. Finally, if the expression is a polynomial, the number of terms can help you name the polynomial. If the polynomial has one term, it's called a monomial. A polynomial with two terms is called a binomial, and if it has three terms, it's called a trinomial. So monomial, one term, meaning there's no addition or subtraction. So 15y squared is a monomial. Negative 2 is another monomial. Binomials, two terms separated by plus or minus. So 16m minus 25, 7h to the ninth plus a half. Trinomials are when you have three terms separated by plus or minus. So 12 minus 3k squared plus 5k, or x squared minus 15x plus 36. Factoring quadratic expressions. Kelly wants to find a shortcut to factor 2x squared plus 7x plus 6. She knows that 2x squared and 6 go into the rectangle in the location shown at right. She also remembers Casey's pattern for diagonals. Without actually factoring yet, what do you know about the two missing parts of the generic rectangle? Well, because we have this diagonal that has a product of 12x squared, we know that the missing diagonal also has to have a product of 12x squared. So we can use a diamond problem to help us figure this out. We know the product needs to be 12x squared. We also know that we need to have a sum of 7x. These two items have to add up to this middle term, 7x. So our diamond problem that we need to solve is a product of 12x squared, a sum of 7x. So we need two numbers that multiply to 12 but add to 7. That's 3 and 4. And we need x's with them so that we get x squared when we multiply and 7x when we add. So now we can fill in our generic rectangle. We know 2x squared, the first term goes in the lower left, 6, the last term goes in the upper right, and then our diamond problem just helped us to figure out we want 3x and 4x. So now we look at each row and pull out the common factors. So 3x and 6 are both divisible by 3. 2x squared and 4x are both divisible by 2x. 2x squared and 3x both have an x, and x times 2x is 2x squared, x times 3 is 3x. 4x and 6 are both even, meaning they're divisible by 2, and 2 times 2x is 4x, 2 times 3 is 6. So our factored form is 2x plus 3 times x plus 2. So this is why you learned diamond problems and why you've been practicing them for so long. They're going to help you to factor trinomials. So you're going to find the product of the first and last term, because the first term goes in the lower left of a generic rectangle, the last term goes in the upper right, and we know that the right diagonal and the left diagonal have the same product all the time. So if we find the product of these two, we fill it into the top of the diamond. This middle term is always the sum, so it goes into the bottom of the diamond, and then we figure it out. We take these two answers then that we find, and we put them in the two remaining spaces in the generic rectangle. They go on the left diagonal. Then we have a completed generic rectangle that we're able to factor out the GCF of each row and column in order to completely factor. So let's use that process to factor 2x squared plus 5x plus 3. So we start to build our generic rectangle. Our first term goes in the lower left, our last term goes in the upper right. We set up a diamond problem. So the product of these two is 6x squared. The sum we need is 5x. So we need to think of two numbers that multiply to 6 but add to 5. That's 3x and 2x. So we fill those into the remaining slots in the generic rectangle, and then we start factoring. 3x and 3 are both divisible by 3. 2x squared and 2x are both divisible by 2x. 3x and 2x squared are both divisible by x. 2x and 3 are both divisible by 1. So our factored form is 2x plus 3 times x plus 1 equals 2x squared plus 5x plus 3. Miguel wants to use a generic rectangle to factor 3x squared plus 10x plus 8. He knows that 3x squared and 8 go into the rectangle in the location shown at right. Finish the rectangle by deciding how to place the 10x terms. Okay, well this diagonal has a product of 24x squared. So we know that our other diagonal will also have to have a product of 24x squared. So we set up a diamond problem. Our product is 24x squared. Our sum is 10x. So we need two numbers that multiply to 24 but add to 10. So we think through the possibilities. You've got 12 and 2, but that would add to 14. You've got 3 and 8, but that would add to 11. 6 and 4, multiply to 24, and that works. So you want 6x and 4x. So then we can factor out, these are both even, so they're divisible by 2. These are both divisible by x. Both divisible by 3x. Both divisible by 4. So we get 3x plus 4 times x plus 2. And that's our factored form. So to factor, you're going to put your first term in the lower left, last term in the upper right. Find their product. You know that the other diagonal has to have the same product. So put that into a diamond problem. Take the middle term, put it in as the sum. Solve the diamond. Take these two and put them into the generic rectangle. Factor out from each row and column. And there's your factored form.